I'll be right there, Jenna. I just gotta open 6. Yeah. There we go. Okay. Good afternoon, guys. Hope you're doing all right. Okay, I know we're a little past time here, but I want to just give people a chance to show for today. I haven't gotten many notifications or any notifications, so I think it's supposed to be a full house. So let's just give people another minute or two. All right, I know we're still one shy, but let's go ahead and start chatting at least. So as promised, I want to devote most of today to review. I have 3 slides I want to show you. The rest are all optional and just designed, so the next set of them are really designed to help me answer any questions you may have or for your own personal review, or if that's helpful. So that's why those are there. And then the final set is if we do have time to get into some new material, it's there. If not, we'll just pick that up after the exam, so that's fine. So let's see how things go. Let me start by showing you what I want to show you. So I wasn't counting this first slide in the 3, so technically 4. So exams next week in class. I am going to give you the whole class time to do the exam in case you need it. I don't know that you will need it, but I just prefer to not plan anything else for that time period. I'm saying to please be sure to have access to your, to your note sheet. I think we talked about having a note sheet front and back. I hope, no, we did not. You may have a note sheet front and back if you so desire, to bring in for the first part of the exam. First part of the exam will be primarily closed book with the exception of this note sheet front and back. So cram it full, make it typed, make it handwritten, whatever works for you. You'll probably would like to have a printed copy of it available, just for your ease, and also because I'm not sure if you'll be able to access it on the computer, like at the same time that you're accessing your test. So do print it out, or if it's handwritten, obviously you'll just have it. Make sure you have a calculator. I don't want to scare you with that. There's obviously not many things that we're calculating, but I think it's just handy to have one. There were a couple small things that we talked about calculating, like the probability and percent. So just in case, you want to have one there, I think it's good. And the first part will be non-SPSS oriented. It'll just be conceptual information. And it'll be primarily multiple choice. And let's say like this, it will be up to 25 questions in the first part. May not be that many, but that's the max it will be. And of those, no more than 3 fill in the blank. The rest will be multiple choice. So primarily multiple choice with 0, 1, 2, or 3 fill in the blank. Okay, so that's how we'll do the first part. And like I said, for the first part, you have your note sheet, and that's about it. The second part will be primarily on SPSS. You'll be asked to actually run some tests on SPSS and do certain things. So for that part, it will be entirely open book, open note. You of course can't speak to each other. You can speak to me, but it will be open book, open note. Okay, so that'll be the second part. And then the split between the parts will be no worse, like it might be 50-50, it might be 40-60, it might be 60-40. I'll probably put a little more on the first part, honestly, than the second, but not by much. So it'll be a relatively close split.
Dr. McKibben, I have a question. Will we get feedback for the 2 SPSS homeworks we did before the test?
Yes, and I wanted to talk to you about that. Thanks for bringing it up. So, oh, here she is. Okay, so feedback for the first 2, yes. Now, question, and I can do either or. I'm just asking you what order to do things in rather than which, because I'm obviously going to do both. But would it be helpful for me to post answers even before I touch yours to grade them, just so you know immediately what the right way to go was? Or would you rather I just jump in and grade them first and then work to post some answers? Any preference on that?
I think I would benefit more if we had the answers first, just so I can get a little head start before next week.
Okay.
Same.
Same. Okay, I heard a same. Okay. Any objections? Okay, then that's how I'll do it. I'll post answers right away. I'll just write something up for you guys for the questions, and then I'll work through actually getting you grades back. But I'm glad. I think that makes more sense. Let's get you some answers right away. So yes, you will get feedback, and today is Wednesday. I will try to get it sooner than this, but no later than Saturday. Will I get you some good feedback on that? Okay. Hopefully even before that, but let me make sure I get it to you by then, so you have that to look at and some feedback and all that, some good stuff. And we can talk about those today too, if you like. We can talk through any of those that you might want to talk through. So feel free to ask about those. Okay, those are good questions. Okay. So the only things I wanted to show you real quick were, and this is more like informational rather than actually going through it. Let me move this down so I can actually put this in slideshow format. Okay. So these are some symbols for you, just so you're familiar with what they look like. The population mean, the sample mean, the population variance, the population standard deviation, sample variance, sample standard deviation. These are what standard error of the means look like. And you can see some patterns.
Sorry, do we need to be familiar with these for the exam? Like
the symbol?
recognize them? Yeah.
Yeah, so because the symbols could come up in primarily I'd be worried about the first part where the symbol might come up, and I think you just dropped in, right? So you might have missed the first part, second part. The first part's going to be more multiple choice with maybe a few fill in the blank, and it's going to cover more of the conceptual type ideas. And this is where I might ask you, I don't know, how would you get from population variance to population standard deviation or something like that? Or if you had, I don't know, I'm not thinking of a good example right now, but yes, you should be familiar with these. So, and you are allowed a note sheet. You probably missed that too. So these might be good items. This kind of thing might be, good items to put on a note sheet, because I know they're hard to remember. But I was going to just point out real quick that variances seem to have squares, if you've noticed, right? That's the pattern. And the standard error of the means always seem to have these funky little X bars in like kind of the footer there. So that kind of gives you a handle as to what those are. Yeah, so yes. So, and then N is your sample size. So we haven't done too many of these, but these are the ones we've done, and there's one more page of them, but these are going to be more familiar. These are ones you've seen more in your output. So these are the ones you particularly probably want to make sure you have a handle on, right? Because DF is degrees of freedom. Our alpha P stands for probability. Now you're used to seeing it as sig two-tailed, but really that's your p-value, and I think you've probably been reporting it that way. Z is a z-score, z-test. T is a t-score, t-test. And remember that funny symbol means summation. U stands for our Mann-Whitney U-score, and that's for our Wilcoxon-signed rank score. So those are things you've probably seen just a little bit more in the output than the first slide. So like I said before, this isn't because I'm going to ask you major calculation questions. We already said we weren't going to do that, but this is just so you have an understanding of what symbols might come up in the literature, and I'd like you to just be familiar with what might come up there and what they mean. So that's the reasoning, at least, behind knowing some of the symbols. This is the one other slide I wanted to show you before I turn it over to you guys. Now, here's the thing I want to make sure you're comfortable with. And this pertains to part 1 and part 2. I want to make sure you're comfortable with knowing which test you're going to at least be considering. Okay? So primarily the last 2 weeks, we've been talking about the t-test for independent samples and the t-test for dependent samples. Now, with the t-test for independent samples, sure, you might wind up running a Mann-Whitney U. And for the t-test for dependent samples, sure, you might wind up running a Wilcoxon. But these two are the different types, theoretically, of the tests. So in other words, when we talk about 2 independent groups of participants, if we were talking about people with blue eyes versus people with brown eyes, then we would be talking about a t-test for independent samples, 2 independent groups. Whereas if we're talking about the same group of people being tested twice, that's the t-test for dependent samples, right? Like we had the pre-test and the post-test, or people who are first being put under a glucose condition and then being put under a no glucose condition. Either way, you have the same people twice. That's your t-test for dependent samples. So you can see that they're very similar in terms of their characteristics, with the exception of the t-test for independent samples has the 2 groups of participants. The t-test for dependent samples has the same group of participant twice. So now I'm going to answer this question, then I'm going to jump back to the other 2. Will you need to do? No, you do not need to do a z-test or a t-test for a single sample, but I might want you to identify one. So I want you to know what one is. So I think I put in that concept checklist that I posted, like for these, you're not going to ever do one on SPSS or calculate one, of course, but I do want you to recognize it. So that's why I have this chart up here, because if you're comparing a sample to a population, if you see that that's what the game is, then you know you've got one of these 2. You know you have a z-test or a t-test for a single sample. Okay, so the only difference between these 2 is whether or not you know the population variance, whether the population variance is given to you. So that kind of harkens back to the symbols we were just talking about, right? Because if I gave you an example, and I'm just going to fly back for just a second, maybe, if it lets me. Here we go. If I give you an example of comparing a sample to a population, and in there I say, and by the way, sigma squared equals this, or sigma equals that, or even sigma x bar equals 20, then you would know that I know some form of population variance, and it's got to be the z-test. If, on the other hand, I simply gave you something with an S in it, an S squared or an S or an S of X bar, one of those, something with an S in it, then you would know, oh, that's a sample information, that's sample variance. It's not that. It's not the z-test. It must be a t-test for a single sample. So going back to this one more time, in both cases, you know the population mean, you know the mu. In both cases, you're simply comparing a sample to a population. Big difference is this. If you know some sort of sigma, the O with the hat, or O with the little line on it, then you've got a z-test. If you don't and you only know S's, you've got some sort of t-test for a single sample. Okay. So that's the differentiation I wanted to make for you, because I think you guys at this point probably have a good sense for how to differentiate t-test for independent, and if I fail the assumptions, I'm going to a Mann-Whitney. T-test for dependent, if I fail the assumptions, I'm going to a Wilcoxon. I think you've got that part, I suspect, down. It's this part I wanted to make sure you had as well. Okay. Let me, like I said, I have other slides for inspiration. If there's topics you want to go over, if there's homework you want to go over, just ask away and we'll just start talking about things.
I think it would be helpful if you like showed us what the slides are first, and then we can see if they're like on the same lines of the questions we were
Of the
thinking.
kind of questions you're thinking? Of course, I'd be happy to do that, sure. So I started off with some slides about the normal distributions and z-scores. And going back all the way to the standard deviation, which is the average amount the values of scores differ from the mean, right? And then we talked a little bit about the normal curve, how the percentages of the normal curve are laid out. If you remember it, with the normal curve, we always talk in terms of standard deviations away from the mean and what percent of the population lies under the curve, given how many standard deviations you are from the mean. And similarly, we have the 68, 95, 99.7 rule that gives us a sense for if we're one standard deviation up or down, we cover 68% of the population. If we're two up or down, we got 95% of the population. If we're three up or down, we got 99.7% of the population. Okay, so I then go on to talk about z-scores and going through those pieces again. I can do that if that's helpful. I have a whole, I basically go through a lot of what we talked about earlier, just kind of starting at this point and then working my way forward through the inferential tests, the confidence intervals, all those pieces. So I'm happy to just kind of roll through those if that's helpful, but I don't want to just sit here and bore you if this is stuff that's not helpful. So I'm trying to decide how to approach this. Do you want to like take a few to like look at either the slides or look at the concept checklist and see what you might want me to go through? Do you want me to just kind of go through the whole thing? Any votes for anything?
I think it would be helpful for you to go through the whole thing, but that's just me. And I did pull out like some particular things from the checklist that I was still like iffy on, but I think I would benefit from, yeah.
Okay. Any other thoughts, or?
Yeah, could you do the whole thing, especially because the exam's next week?
Yeah, of course. Yeah, that's no problem. I just didn't want to like bore you to tears if it's stuff that you felt wasn't going to be on the topic of your questions. But yes, I'm more than happy to. So let's do it. Let's talk through this. Okay, so z-scores. Z-scores, if you remember, are standardized scores. And really, the main point of z-scores that I want you to take away is it tells you how many standard deviations you are away from the mean. So a z-score of +1 means you're 1 standard deviation above the mean. A z-score of -1 tells you you're 1 standard deviation below the mean. And we can just follow that pattern. A z-score of 1.64 means I'm 1.64 standard deviations above. A z-score of -3.23, I'm 3.23 standard deviations below. Right? So it's just the number telling you how many standard deviations away you are. The positive or negative tells you whether you're above or below. Okay.
Can you offer like a conceptual example of like maybe like a problem where you would want to look at a z-score?
That's a good question. Let me think about that. Well, that's a little bit tough off the top of my head, but I'm trying to think of something that would embrace that. I mean, I guess a good problem would be if you're trying to compare two scores that are not on the same scale, right? So someone got an 84 out of 112 with a standard deviation of 12. And someone else got a score of 82, and that one has on a scale up to 150, and that one has a standard deviation of 15. It would be hard to compare those scores just by themselves. That's a lot of numbers coming at you, and you're not sure what to do with them. But if I also told you the mean and the standard deviation, you could convert those scores to a z-score and then compare the z-scores, because the z-score standardizes everything. So let's take a better example. Let's say that a person has a score of 60, the mean is 50, the standard deviation is 10, just to keep it kind of easy. Then we could convert that to a z-score by taking the score of 60 minus the mean of 50 over the standard deviation of 10, and we would suddenly know that the z is 1. They were really 1 standard deviation above the mean. And similarly, if we had someone else with a, and I'll just make this super kind of, well, I'll make it more interesting than that, I guess. They have a score of 45, the mean is 60, the standard deviation is 15. So now we take the 45 minus 60, we get -15, divided by 15, we get a -1. So now we can suddenly compare these two people's scores, whereas it might have been a little bit of a challenge before. You can see that one's 1 standard deviation above the mean, another's a standard deviation below the mean. So that might be, hopefully that's kind of a real life example of the kind you had in mind.
That's helpful. Thank you.
Yeah. So, okay. So those are your z-scores. Oh yeah, and here's, I could have just flipped to the next slide. I forgot I had an example sitting here. So yeah, I can go through this one too. Jacob spoke to other children 8 times in an hour. The mean number of times children speak is 12, and the standard deviation is 4. So to change the raw score to a z-score, we take the raw minus the mean, or 8 minus 12 is -4. Divide by the standard deviation, which is 4, get -1. And you can see that they are, that our friend Jacob is sitting right over here by the -1. And all of these people to the right of Jacob speak more than Jacob? So in this case, it would be the 50% over here, all to the right, plus the 34% over here. So about 84% of people speak more than Jacob.
Could you just go back to the previous slide real quick?
Yeah.
All right, thank you.
Sure.
Is this like the type of question we would see on the exam, like as far as like the calculations you were talking about?
This could be a kind of calculation that could come up. I know we didn't go any deeper than this, that we didn't calculate standard deviations by hand or variances by hand, but we did do probability. And gosh, let me actually pull up my, kind of want to pull up my concept checklist at the same time that we're talking, just to make sure. But I believe Z-score was on the concept checklist. So anyhow, that's the kind of thing. I'll pull it up later and we can chat. But that's the kind of thing, yeah, I had in mind. So not much more than this, though. This is about as far as we go. Okay. All right, so here's that again. Here's that again. And then we can go through other examples too. But if you'd like me to go through this one, let me know. Otherwise, I think I'm going to move past this one because we've already talked through a couple. And I want to show you something else instead. Okay. We'll look at this one. This is the third one, just to make sure we're feeling good about it. So in this case, we've got John, who spends, and this is of course very made up data, who spends 5 hours on the web per day, I guess we'll say, per week maybe. And of the mean is 6, standard deviation 2. Over here we have 4.5 for Katie, 4 for the mean, standard deviation of 1. And so we would do the same thing again. We would take 5 minus 6 divided by 2, and we would get negative 1/2. 4.5 minus 4 gives us 0.5. Divided by 1 still gives us 0.5, so positive 1/2. And there's the math for you. Sorry, my 2's moved over. That 2 should be under the negative 1 here. It just got moved over a little bit. And same over here, the 1s should be shifted a little bit. So negative 0.5 versus 0.5. And so we see Katie compared to her population uses the web more than John does compared to his population. So even though this John's number is higher, the Z-score is higher for Katie. Okay. Yeah, let me, all right, I'm gonna pull up this checklist super quick. I don't wanna put extra things on you that you don't have to know. I just want to check if if one particular item is on here. I think if it's on I think we did discuss this, but I just want to be sure because I might have changed it. Okay. No. Okay. So for Z-scores, actually, I was saying know what Z-scores are, know what their mean and standard deviation are. So the mean for a Z-score is always 0 and the standard deviation is always 1. But I did not say that you need to know a z-table. So let's not worry about that little piece right there. It can be helpful to understand that if you're struggling with understanding what t-scores are and how this all works. But so I'll show it to you, but I don't want you to worry about it. So this is what a z-table would actually look like in real life. And the basic idea is that you can actually get an exact conversion between your z-score and the percent in the tail. So that's kind of cool, that I can say that, oh, this person's z-score is 0.52. What does that really mean? I mean, I know they're about half a standard deviation of, above the mean, but what does that mean? Well, it means they're in the top 30.15%. Or if they had a negative 0.52, it would mean that they were in the bottom 30.15%. So I think that kind of understanding can just be kind of helpful to know, to have a better sense for what z-scores are and how they work.
Can you repeat that one thing that you said like 2 minutes ago? You said a z-score, like the mean is always
0 and the standard deviation is always 1. Yep. Mean is always 0, standard deviation is always 1 for a z-score. Which should make some, I'm going to flip back here, should make some intuitive sense here, because we're talking about being +1 SD, +2 SD, or -1 SD, -2 SD. So it makes sense that standard deviation is actually a unit of 1. And then the mean is just sitting in the middle at 0, going either to the positive or to the negative. Okay, all right. So the z-table is kind of cool. Like I said, we're not really using that in this class, because we're not really dealing with that kind of hand stuff. But it is interesting just to see that you can go from a z-score to a percent, and from a percent to a z-score. Just like you can go from a raw score to a z-score, and you can go from, and we won't do this calculation because you wouldn't have to do this calculation, but I'll just tell you that you can also go from, a z to a raw, or from a raw to a z. So we were talking about taking raw scores and converting them to z-scores to compare them. But let's say someone told you, oh, I got a z-score of 1.64. And you're like, well, what's your raw score? And you want to find out. You could actually use a formula to figure that out too. Again, as long as you know the mean and standard deviation. Okay. So now, and just pop in with, chat in with questions, or talk out with questions anytime you have them. But I'm going to press on to some inferential statistics and hypothesis testing. Okay. So here's our normal curve once again. And the fun part about hypothesis testing is that you get to set your alpha. You get to say where your cutoff point is. Now, that's within a certain degree of, you're allowed, but with certain limitations. In other words, people generally don't make their alpha bigger than 0.05 or 5%, right? 0.05, 5%, same deal. So people generally don't make their alpha bigger than this. They might make it smaller, such as 0.01 or 0.001, but not bigger. Okay. So when we are trying to understand whether or not people who took, and we'll say this was our hypothesis, that people who take vitamin and vegemin will have much higher energy levels than those in the regular population. Let's say that's our hypothesis. Well, this is what we're looking for. We're looking for the mean of vitamin and vegemin, and the mean for a normal curve is kind of right down the center. right? And the mean for the population is right down here by 100. We're looking for this mean to be far enough away from the population mean such that it falls in the top 5% of the tail. So this is the top 5% of the tail, right, in gray. We want this mean to fall in this gray region. And I could have had this kind of falls into it. I could have shifted it over even a little bit more to make it more dramatic. But as long as this mean falls in that top 5%, we get to reject the null. If it falls anywhere else, even if it falls all the way down here, suggesting that it is really produces much lower energy levels, we don't get to reject the null. Because we made a claim at the beginning, we made a one-tailed or directional claim that it was going to be higher. Once we make that claim, that's the only thing we can look at, is higher. Okay. On the other hand, if I made the claim that vitamin vegemin decreases energy levels, now we're on this side of the curve. Now I want to be in the bottom 5%. I want this mean to be very low compared to the population. In this case, it looks like it is very low, and it pretty much just about falls into this gray region. Again, I could have moved it over a little bit to be more dramatic, but it pretty much falls into this gray region. And so in this case, we would also be able to reject our null, because it does look like it produces lower energy levels. And again, same situation. This is still one-tailed and directional. If our mean had been super high, doesn't matter. We can't reject the null. Now, if you don't like that game, then there's one more I can offer you, and that's this one. This is the two-tailed non-directional. So if you don't know, vitamin vegemin's so new, I don't know. I think it's going to affect energy levels, but I'm not sure how. I'm not sure if it's going to make them higher or lower. I just think they're going to be different. Then you can split your alpha into two pieces. I'll put half of it here on the top and half of it here in the bottom. Now I can fall in either of these two gray regions, which is a good deal. But the bad part of the deal is that now I have to be further in the tail. Before, if you noticed, I could be, all I had to do was pass 1.64 or negative 1.64 on my z-scale. Now I've got to pass 1.96 because I only have 2.5% here, not 5%. 5% may be over here. I only have 2.5% that I get to fall in. So that's the cost benefit kind of situation.
Dr. McKibben, is the 1.96 the standard deviation for the z-score then?
Yes.
Okay.
Yeah, it is. In other words, this is saying that you've got to be 1.96, which is awfully close to 2, right? Standard deviations more than that above the mean, or less than negative 1.96 standard deviations below the mean. So you can be either above or below, but you've got to now be higher above or lower below. If you're anywhere in the middle, in this 95% in the middle, you don't get to reject. Okay. All right. So this brings us to, I think I have both of them. Yeah, I'm just going to skip to the second one of these tables, so I like it a little better. this brings us to the elements of hypothesis testing, the correct and incorrect decisions table. So what we're talking about here is whether or not we made the correct decision, right? We decide to reject or we decide not to reject. Did we make a correct decision or did we get an error? The truth is we'll never know, because this true state of the world is unknown in practice. So in other words, whether or not the null hypothesis is true, whether or not there is an effect, is unknown. That's what we're trying to find out. That's what we're trying to show. But we can only show it with a certain level of probability. We can never be sure. Just like, and I think I used this example before, but if not, here you go. Just like if you are in a courtroom and it's your job to be a juror, let's say, and decide if someone is, you're going to convict someone or not convict someone. Well, they are either guilty or innocent. You will probably never know for sure which one they are. That's the true state of the world that you will probably never know. So let's choose that someone is innocent, okay? Let's suppose that the null hypothesis is true, there's no effect, the person is innocent. If you do not reject the null, and the null is true, if you're in this box, you made a correct decision. How often will you do this? 1 minus alpha % of the time. So if you typically set your alpha to 0.05, then you will make this correct decision 95% of the time, which is great news. Unfortunately, the other 5% of the time, you will convict the innocent. You will reject the null, even though the null was true. That's what we call a type 1 error, or a false positive, or alpha. That's the kind of error we truly try to avoid. In psychology, in the behavioral sciences, we hate this error. We hate the type 1 false positive error. We really try not to do it. And the rationale is that, you know, we don't want to change a practice that's already working for a better practice and then find out the better practice was really not better. Okay. Now let's say that the person's actually guilty, that the null hypothesis is not true, that there's actually an effect. If the null hypothesis is not true, if there's an effect and we reject the null, we've made a correct decision. Once again, that's wonderful. In fact, that's the correct decision that we are most hoping for. This box right here in the upper left is the one we really want, because that means we found an effect. That happens with probability power, which usually we try our best to keep at 80% or better. And I think I mentioned that that doesn't sound very good. 80% doesn't sound very wonderful. I mean, you might want 90 or 95, but the problem is to get 90 or 95, you typically have to have a rather large sample size. And often in psychology, that's prohibitive. You know, it just isn't feasible. Okay. If you do not reject the null and there was an effect, you did not convict the guilty, they go free, and you have made a type 2 error, or 1 minus power, false negative. This happens around 20% of the time. If this is 80, then this is going to be 20, 1 minus power. Okay. So if this type 2 error is really, you know, we don't like it because we missed finding our effect. But we're more willing to tolerate this type 2 error than this type 1 error. That's why we keep this one real low at 5, and we might allow this one to go up to 20. Now, you might be wondering, what if I'm in a situation where it really is worse to make the type 2 error? And this happens in medicine a lot, where it's worse to make the type 2 error. You don't want false negatives. You know, if someone comes in to test for coronavirus, let's say, you don't want them to walk away and say, oh, no, you're fine, and that be a false negative. So in medicine, it's a little bit different. If they really had it, you wouldn't want them to walk away and say, oh, you're fine, if they really had it. So yeah, so that's medicine. That's a little different. But in our field, we're more willing to tolerate type 2 than type 1. Okay. All right, let's press on. Okay. So let's talk a little bit about power, effect size, and confidence intervals, because those also tend to be kind of tricky issues. So we're just talking about power, and if you remember, power is the probability of finding an effect if there really is an effect to be found. How likely am I to find an effect if there really is a difference, if there really is an effect out there? Okay. All right. So what contributes to power? Well, I already told you the biggest thing that contributes to power is sample size. Biggest thing that contributes to power is sample size. Larger N means more power. Effect size, larger effect means more power, is another one. But it's difficult to increase our effect size. In other words, going back to our vitamin of regimen example, it's true that if I could get people to score 2 standard deviations above the mean rather than just 1.5, that's more powerful. I'm more likely to see that effect. But how do I control that? I really can't. It's really very difficult to do so. The other thing that we can do to increase our power is to increase our alpha. But remember, we don't want to do this. We like our alpha nice and small. We want to keep our type 1 error really small, so we don't usually do it. So while there's 3 ways to actually increase power, we only focus on the first way. Primarily focus on sample size. It's the best way to get more power. If you have power, if you have high power, you have a greater chance of getting your significant result, of rejecting the null. If you don't have enough power, well, your study might have actually been a waste of time, because what if you found out, I mean, again, this is something you'll never know, but if you ran 40 subjects and you had only a power of 60%, what if you had run that extra 20 subjects that would have given you, or that extra 30 subjects that would have given you the power of 80% that you needed? Maybe your result would have been different. Maybe you would have found an effect, whereas you didn't with just the 40. So you put all this time and resource into finding something, and the only reason you didn't find it is because you didn't have enough power. Okay. So we already talked about the most common way to increase power is to increase sample size. And this doesn't come up until the next semester, really, but if you happen to find yourself in a place where you want to conduct a power analysis, you want to figure out your power for a particular study, these are some free options, free software programs that'll do that for you. So at the end of the day, how many research participants should be included in the research? Well, it depends on a power analysis, and it depends on what you can actually do, right? Practicality must be balanced with the increased power that accompanies a large sample. We've got to be practical, right? Students have to graduate, research has to end at some point, grants run out, all kinds of things. So we have to be reasonable. Okay. So let's turn our attention a little bit to talk a little bit more about effect size. Okay. Effect size is the amount that two populations do not overlap. The amount that two populations do not overlap. So in other words, this difference between the mean here of population 2 and the mean here of population 1 is really the effect size. That difference between 200 and 220, that's the effect size here. Okay. And an effect size is really nice because it's standardized, just like a z-score is standardized. So which means it's comparable across studies. Okay. So you get to actually evaluate the size of an effect. Okay. So there's two ways that you can actually impact effect size. You can increase effect size. The one is obvious, increase the size of the effect, make larger mean differences. The other is a little bit less so. It's to decrease the variability, decrease the spread, or decrease the differences between people in the same group. So let me show you this one. This is the first one. And we can see, of course, that this has a larger effect size, a bigger difference between the means than does this one. All right. However, over here, this is the same. We're comparing 35 to 50. We're comparing 35 to 50. Yet this one looks like it has, the one on the right, looks like it has a larger effect size. Why is that? Because the standard deviations are smaller on the right side. Because there's less variance, less spread. So there's less overlap. Okay. Now, you might see several different effect size measures out there in the literature, like Cohen's D, Pearson's R, odds ratio, risk rates. And Pearson's R is a good one because most of us have seen correlations out there somewhere. And so it's a good way to think of an effect size. And just to give you a little bit of an intuitive sense of the correlation coefficient R, and we're not getting into that now, we'll talk about it more later. But here you can see when everything lines up perfectly, we have an R equals 1 or an R equals -1. Those are really strong effect sizes. And it dips down to 0 when there's almost no relationship between the variables. Okay. Showing you the next formula just for information purposes. You do not need to know how to calculate this. This is just so you can see how it might work. Right, so in order to get a D, we might look at the mean difference over what we would look at some form of a standard deviation, if you will, some measure of spread, which we would calculate in this way. So just to give you a sense, D looks at the means versus the spread, which a lot of our statistics do. Okay. This is more interesting and more worthwhile, again, just to look at what's a small effect, what's a medium effect, what's a large effect. Just to give you a sense for it. Yes, there's a question coming up, so hang on. Oh, yeah. Let me answer this question because yeah, let me just finish effect size, then I'll cover that, okay? Let me just finish off the effect size, then I'll get to this. And it's a little different. It's a little bit before we hit this. So anyhow, the main advantage of effect sizes is that you can actually compare the actual sizes of effects rather than just always saying significant, not significant. So it's kind of a nicer, less categorical decision. Okay, so let me answer this question now. So what about floor and ceiling effects? And what is the impact on distribution? So basically, a floor effect, I'm going to move myself back into view. Okay, that's better. A floor effect is when all the scores pile down low by the floor. So if you had a test and almost all students got 0s or 10s or 20s out of 100, that would be a floor effect. A ceiling effect are when most of the scores hit the ceiling or way up high. So again, if you had a test and most students got a 90 or 95 or 100, that might be a ceiling effect. And so the way it works is that they're related to skewness. That's what I mean by how it relates to distributions, its impact on distribution. Because when you have a floor effect, you have most people on the floor, right? So this is the frequency distribution for people on the floor, a lot of people on the floor, and then it dips down, excuse me, as you get higher and higher scores. So if you follow that tail out to the right for a floor effect, you will see it's a positive skew. Whereas with the ceiling effect, most scores are all the way to the right over here. And then it dips down to the left. So that tail is going to the, oh, my mirror's on. This is awful. You're seeing the reverse of what I want you to see. Can I fix that? Shoot. Sorry. I'll say it, but I won't show it because that's just going to make it worse. So if you have a whole bunch of people up on the ceiling, up getting 90s, 95s, 100, then as you walk to the left to lower scores, that ceiling effect goes to a negative skew because you're going to the left with your tail. And I keep pointing when I shouldn't. Okay, so ceiling effect, negative skew. Floor effect, positive skew. And I can certainly switch gears at any point and show you those slides as well if you want to like look at a picture of those. It was further back. We can certainly look at that. Okay. If at any point you want me to switch or this isn't, you know, this you kind of already know this piece, just let me know. But I'll kind of keep carrying on unless you want otherwise. So okay, let's talk about the characteristics of the sampling distribution of means. So we talked a little bit about the sampling distribution of means. And we saw that, I think I showed you that dragon video, right? The dragon video and the bunny video that kind of shows, there we go, that kind of shows the importance of the central limit theorem. So what we're talking about is that if you take many, many, many samples from a population, and you take the mean from each of those samples and put those into a frequency distribution, you will get a sampling distribution of means. That sampling distribution of means will be more normal and more narrow than the population. So the mean of the sampling distribution of means, and these formulas I don't expect you to know. I just want to put that out there. You don't need to know these, but I would like you to just kind of see how they work. The mean is just our population mean. The variance is just our population variance over n. And this one you should be familiar with the name of. The standard error of the mean is just our standard deviation over the square root of n. So you don't worry about the formulas, but you should have a sense for this idea of standard error of the mean or standard deviation of the sampling distribution of mean. Okay. So again, the idea here, it looks like I just want to make sure I cover enough of that before we press on. The idea here is that if you take many, many, many samples from a population, for each sample, you just take the mean, and then you plot those means on a frequency distribution. As long as your samples, as long as either your population is normal or those sample sizes are at least 30, you will get a very, very normal and narrow distribution. Okay. All right. So let's talk a little bit about confidence intervals, because that is something you're reporting on. So hopefully this will be a little bit more real life to you. And these are a range of values that we can be confident contain the true value of the population mean. Okay, so in this case, if we obtain many, many samples and construct confidence intervals for each of them, 95% of the confidence intervals will contain the population mean. Which means we can be 95% confident that our interval contains the population mean. So really, confidence intervals, way back when we were talking about those significance tests and we were talking about being in the gray region, this is the same thing. This is really just the same thing, except now we're talking about the inside rather than the outside. So in other words, whereas a significance test says, hey, are you on the outside? Oh, yeah, you're on the outside, you get to reject. What a confidence interval says, are you not on the inside? Are you not on the inside? Oh, you're not on the inside? Great. Then you're on the outside and you get to reject. It's just asking the question with a negative, but it's the same answer. Okay. So let me show you a little bit more about confidence intervals. Here is an example of 20 confidence intervals, 20 studies that were conducted with the population mean, the true population mean being in the center, down this blue line. And what we have is 19 of our confidence intervals out of the 20 cross the blue line, contain the population mean. Only this confidence interval doesn't. So this would be an example of the 5% type 1 error. In other words, if you had 20 studies, right? And we knew that the true population mean, that was really in the center. And you're measuring and you're measuring in each of these studies. One of them you would find to be significantly different from the population mean because it doesn't contain it. And you'd be wrong. This is that type 1 error right here. So it really is the same sort of beast as the significance, just looking at it from the opposite vantage point. Okay. So here's just another example. I guess this is from Damjan et al. 1998, and it's a conditioned sperm release in Japanese quail. So if the true mean is 15 million sperm, and the sample mean is 17 million sperm, if you get 12 to 22 million in your 95% confidence interval, that contains the true value of 15. But if you get, let's say, 16 to 18 for your confidence interval, you're missing the true value of 15. And CIs, confidence intervals, are constructed so 95% of the time they contain the true value. Okay. Here's just another example showing you many, 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 many studies that were run and showing you that these 5 that don't hit the mean are falling away, right? They're the ones, they're your type 1 error. They're the ones where there is no effect, but you're finding one. Okay. And this is just one more look at confidence intervals. One where we hit it, one where we miss. Okay. And this would be, I'll just show this to you again, not something you need to be able to calculate, but it is how you would get to a 95% confidence interval. Notice this 1.96 making another appearance here, just like we saw in our 2-tail test. And notice the SEM making an appearance. Okay, all right. That's how one would calculate a 95% confidence interval. You just get them on your SPSS, so that is good. The main takeaway about confidence intervals, I would say, is remember they're just confidence intervals. Remember, we already, the mu, the population mean already exists, so we should always talk about confidence intervals with confidence, not with probability. That's one of the main takeaways. Okay. All right. So this is kind of a pulling it together moment that I had put up here. And we have the post-traumatic checklist with a mean of 30.12 and a standard deviation of 15 in a non-traumatized general population sample. In this case, we want to know if the people in the community of Moore, Oklahoma will have significantly different scores on the PCL than a general population sample. We sample 25 people in Moore, Oklahoma who complete the PCL. We obtain a sample mean of 36. Okay. Our alternative, based on just the information in here, is people in the community of Moore, Oklahoma will have different PCL scores than the general population. So what am I comparing? I'm comparing a sample to a population. Sample to a population, right? People in the community of Moore, Oklahoma, that's my sample. General population. And I just add the word not for the null, of course. Excuse me. So here's my question to you, since this is a pulling it together moment. Which test is appropriate here? Not running anything on SPSS, just in terms of your first thought. We talked about 4 major tests, right? The Z-test, the T-test for a single sample, T-test for independent samples, and T-test for a dependent sample. Of those 4, based on the information you're given, based on the fact that we just said we're comparing a sample to a population, which of those 4 do you think you might run here? Oops, excuse me. Close. The thought was T-test for a single sample. It's really close. And let me tell you why it's actually the Z-test. Because we're given this population standard deviation right here. See that sigma? If you see a sigma in an example, it means we know something about population spread. I could just square this to get population variance, right? So I've got that. So because this is here, it's actually a Z-test. But you're right about sample versus population, and that's the tricky part, is knowing the difference between Z-test and T-test for a single sample. Had this been S instead of sigma, you would have been right on. It would have been T-test for a single sample. Okay. All right. We already talked about this. This is just differentiating is was it one tail or two tail. And I think we got the idea, but let's just talk about it real quick. If we're talking about different, then we're talking about two-tailed, right? Because we didn't say if it's going to be higher or lower. So it's two-tailed, it's non-directional. So we're in this boat.
I have a question that came up when I was doing the homework.
Of course, yeah.
If it's a two-tailed, and then there is a significant difference, would you go back and look at the direction and get a new p-value to say that there's a significant difference and like say it's increasing, one group is increasing?
That's a great question. Yeah, I love that question. So the official answer, the statistical answer is no, you shouldn't do that because you said you're just going to look at differences.
Mhm.
The practical answer is, yeah, people do it all the time. So, so statistically, you only bargain to look at difference. That's probably all you should report on. But do people actually then go and talk about, yes, this was an increase? Yes, it absolutely is so commonplace that I don't think most people even really recognize that that's probably not the right approach.
Thank you.
Yeah, of course. Okay. So again, we could go through, we could calculate a confidence interval. I want to get to a point here. Yes, and this is what I was talking about before, about the confidence interval versus the significance test. And how they're really telling you the same thing. Significance test is just asking, am I on the outside? Yep, great, I can reject. Am I not on the inside? That means I'm on the outside. Great, I can reject. Okay. And this would just show you that the confidence interval and the z-test are essentially telling you the same thing, that you landed right around here. Just outside of hitting inside this gray area. Okay.
Quick question.
Yeah.
You had mentioned if we had the sigma, it'd be a z-test, but if it was what symbol, it'd be the independent test, t-test?
Yeah, the t-test for a single sample, yeah, that would have been an S.
Okay, thank you.
Yes, of course. Okay, so then we have, so now we're kind of pushing into inferential testing. And now we're talking a little bit more about z-tests. And again, I think you guys tell me otherwise, but I feel like the null alternative is coming along nicely. So we can talk it through though. I mean, people in the community of Moore will have different PCL scores, or people in the community of Moore, Oklahoma will not have different PCL scores. And again, we get this directly from what the researcher believes. Okay, all right. If we had changed it such that the researcher believes that people in Moore would have higher PCL scores than the general population, and by the way, that's a post-traumatic checklist, then people in the community of Moore, Oklahoma will have higher, or people in the community of Moore, Oklahoma will not have higher. Just taking it directly from what we have there. Okay. And of course, if we said higher, that would be one-tailed because we gave a direction. Okay. Okay. So here's where one-tailed and two-tailed gets kind of interesting. So I want to show you this, because if this z is 1.80, right? And had this been two-tailed, well, we know the cutoff is 1.96 in terms of standard deviations, in terms of z-scores. 1.80 falls just shy of that, just to the left of that. Just to the left of that. So we wouldn't reject. However, if we're in one-tailed land, and if we had made the correct predictive direction, then here we have 1.64. 1.80 lies to the right of that in the gray region. So again, in this example here, we would not reject. In this example here, we would reject. Okay, and someone asked a really good question that I'm going to capitalize on right now about, well, how does this work with the p-values, and why do you divide those p-values by 2 when you have a one-tailed test? Okay, so p is our probability of making a type 1 error. We're trying to keep our p's low. So when we go from here, from this 1.96 cutoff to here, this 1.64 cutoff, it means we have more room. In other words, really, when they're giving you a p-value for this two-tailed test, they're accounting for this 2.5%. You get to divide that by 2. You get to have a smaller p-value, or, in other words, a larger gray area for your one-tailed test.
And I'm sorry, does SPSS automatically do that, or do we have to divide?
SPSS automatically always gives you two-tailed. So if you need one-tailed, you have to divide by 2.
Okay.
Yeah. Don't worry about it if you didn't get to that little piece on the homework. You know, it's just a little thing, but you'll get it. And that's the idea, that yes, SPSS will only give you two-tailed almost all the time, with one small exception we'll talk about later in the semester, and you divide if you need the one-tailed. Okay. Okay. So here we are back to z-test versus t-test for a single sample. Both compare a sample mean to a population mean. The population mean is known for both. The mu is known for both. But in z-test, we know a sigma, some form of a sigma. In t-test for a single sample, we do not know a sigma. We estimate sigma using S, or S squared. Okay. All right. I think someone else had a question about degrees of freedom too. So let me take a moment on degrees of freedom, because this only starts to come up when we have our t-test. And it is true, it does come up for all of the ones you've been working with. The t-test for the independent sample, the t-test for the dependent sample. It comes up with the Mann-Whitney-U and the Wilcoxon. So it's good to know about, oh no, actually, sorry. Comes up with the 2 t-tests. So it's good to know about degrees of freedom. Degrees of freedom has to do with the number of scores that are free to vary. So in other words, I think I gave you this baseball example before. So if, I'm trying to think if there's another way to go through it, but it has to do with the idea. I'll give you the more straightforward one now rather than the baseball one. It has to do the idea that you're always estimating a mean, right? You're always figuring out a mean. So that means that only all scores but 1 are free to vary. In other words, if I told you that the mean is 30, and I told you the first score is 10, the second score is 20, can the third score be anything it wants to be, assuming there's only 3 scores? Can the third score be anything it wants to be? No. It's got to be a number such that when I add up my scores and divide by 3, it equals 30. It's no longer free to vary. And so that's why in the t-test for dependent samples, we lose a degree of freedom. In the t-test for independent samples, we lose a degree of freedom for each sample, for each of our 2 samples, or 2 degrees of freedom, because we are doing the mean calculation twice. We are estimating twice, and so there are 2 scores that are not free to vary, 1 for each sample. Okay. And okay. So we've been talking a lot about the z-test and the z-score and the normal distribution. Well, the thing is, the t-test distribution is a little bit not normal. The more n you have, which means the more degrees of freedom you have, because degrees of freedom is just taking away one n, right? N minus 1, sample size minus 1. So the bigger your sample, the bigger your degrees of freedom, the closer t looks to normal. Okay. So here's an example. Here's your normal distribution in black. And you can see over here is a t distribution for a degrees of freedom of 2 or an n of 3. Here's your t distribution for degrees of freedom of 20 or n of 21. Okay. And I'm just going past this because you get your t scale, you get your t scores automatically given to you through SPSS, so you don't have to worry about this. Okay. I think we looked at this. I don't think you loved it very much. It's just trying to show you that. I'm just trying to convince you that z-scores and t-scores are really not all that different. But maybe you'll believe me on that. I don't know. They all involved subtracting means on the top, and they all involve a standard error of the mean on the bottom. Okay. And then transforming data. Let's talk about transforming data for just a few minutes. These, I don't expect you to memorize these. These are just interesting pieces of what you can, where you can use different transformation to help yourself out. So if you found yourself having a lot of positive skew in your dependent variable, one thing you could do is take the log of every participant's dependent score. Okay. Or also reduces positive skew or need to stabilize the variance, you could take the square root. And so each of these little transformations have their own purpose, right? 1 over x naturally decreases the impact of really large scores, right? That would make sense. And so you can kind of see, here's a log transformation. Here's a square root transformation. Here's a reciprocal or 1 over x transformation. But as we talked about, transformations are not necessarily the best idea. Transforming the data, people say it helps as often as it hinders the accuracy of what you're doing, because it changes what you're actually testing. So transforming data, I definitely don't recommend doing it for any of the examples that are your test or anything like that. If you decide you want to do some transformations of your actual dissertation data, you know, that's certainly understandable, but this isn't expected for anything we're doing in class or for the exam. But the main idea I wanted you to understand from this is that, you know, it's really good to be thoughtful about transforming your data, because it can make things more messy than clean. Okay. All right. So that's what I had in terms of reviewing pieces. What I'm going to recommend we do now, because it's kind of perfect timing for this, is to take a 10-minute break. Let's hear from our 2 presenters when we get back. And then with the remainder of time, I will turn it over to you for any additional questions that you might want to ask, anything else you'd like me to review. So let's go ahead, take a break now, and then do that. Okay? All right, I'll see you in about 10. Okay, since there's no immediate questions coming my way, I'm going to excuse myself for just a couple minutes and I'll be back. Oh, you just need to get that.
Hi guys, I'm her son.
Thank you, Chris. Okay, I'm not sure if we're all back yet or not. If you could give me a high sign, I can see one of you, but if, okay, thank you. Okay, good, good. Okay, you're back, you're back. Okay, so we might be waiting on one person. Let's just give them one more moment and then we'll get started. Okay, all right. So Lindsay, since you have the t-test for independent samples, would you mind getting us started on with your presentation about that?
Sure, I'm just gonna share my screen.
Okay,
Do you see the PowerPoint?
I do.
Okay, thanks. So the article that I'm presenting on is factors that distinguish college students with depressive symptoms with and without suicidal thoughts by Nair et al. I think there was like 10 authors, so I only included the one here, and it was written in 2013. So to summarize the article, the researchers wanted to determine if specific factors contribute to depressed college students experiencing suicidal ideation. So they did find that depressed college students with a higher degree of hopelessness, anxiety, and depression experience more suicidal ideation, but they did not find significant differences in everyday functioning between the two groups with and without suicidal ideation. So they ran a t-test for independent samples. The independent variable was the response to item 9 on the BDI, which indicates the presence or absence of suicidal ideation. So as I think most of us probably know, the BDI is scored from like 0 to 3, like 0 being like not at all and 3 being like all the time or something like that. So for item 9 though, it's 0 or non-zero because suicidality is so important and serious to look at. And then the dependent variables were all of the scores on each measures that they used, which included the BDI minus item 9, and the anxiety symptom questionnaire, the Beck anxiety inventory, the Beck hopelessness scale, the cognitive and physical functioning questionnaire, and the quality and life enjoyment and satisfaction questionnaire, and then also the GPA scores. So the two groups they included were depressed college students with SI and without SI. They found no significant differences between the two groups on demographic characteristics. The mean BDI scores for the full sample with the 287 participants were 19.46 with a standard deviation of 6.67 for the BDI total score, and then 18.98 with a standard deviation of 6.48 for the BDI total score minus item 9, which was the suicidality item. So they had statistically significant results for substantial depressive symptoms, but they didn't find statistically significant differences between groups in functional impairment, which I'll go into more detail in a future slide. I think they included 8 hypotheses, so I only included 5 here, but basically their null hypotheses was that students with substantial depressive symptoms and suicidality do not have greater total scores on the BDI minus item 9 than those without SI. So they were hypothesizing that students with substantial depressive symptoms and SI would have greater total scores on the BDI minus item 9 than those without. So I just swapped out BDI for BAI and BHS for these 3 hypotheses. So they are the same except for the measure used. And then for the last 2, these are the ones that we're looking at functional impairment. So the null hypothesis was that students with substantial depressive symptoms and SI do not have less life enjoyment and satisfaction than those without. So they were hoping to see that students with, not hoping in general, but hoping to find in the article that students with substantial depressive symptoms and SI have less life enjoyment and satisfaction than those without. And they were hypothesizing that students with SI and substantial depressive symptoms would have lower GPAs as well. So all of these hypotheses are one-tailed because they're specifying the direction of the relationship. And then for the hypotheses that I listed, for 1, 2, and 3, we would reject the null because they did find statistically significant differences between the groups. And just a reminder, those were the BDI, the BAI, and the BHS. And then we would not reject the null for the last 2 hypotheses because the results did not show statistically significant greater functional impairment between the groups. So just to make it a little easier, I included the results table that we can look at together. Like I said, the total sample size was 287 participants, and they all had substantial depressive symptoms. So they had to meet a certain criteria on the BDI before being included. And then they were split into groups with suicidal ideation and without suicidal ideation. So their total mean score for the BDI minus item 9 was 20.61 with the standard deviation of 7.85. And then without suicidal ideation, the mean score was 17.74 with the standard deviation of 4.88. So then if you look over here at the T-scores, you can see that for all of these, sorry, my mouse is a little lagging. For all of these psychiatric outcomes, so all of the measures that we're getting at depression, anxiety, and hopelessness, all of the results were significant. And then for functional outcomes, the results were not significant. So as you can see, they were very similar on cognitive and physical functioning, life satisfaction and enjoyment, and their GPAs were almost the same as well. So the t-test for independent samples was most likely appropriate to use. I don't have all of the raw data in front of me, but assuming they followed all of the assumptions, and there was 2 independent groups, so we can just assume that it was the appropriate test to use. The concerns that I had with the design of the study were that the only way they measured suicidality was just that one item on the BDI. And as we know, there's a lot of variability within suicidality. And although they know the scores, it's still rated 0, 1, 2, or 3 on the BDI, but it's still interesting and important to know exactly where students lie on that. So I think that something more like the Columbia Suicidality Severity Scale would have been more appropriate to use, like an entire suicidality measure rather than just one question on another measure. And that's it. Does anyone have any questions?
Very nice presentation. Thank you.
Thank you.
I'll ask you one quick question.
Uh-oh.
So okay, here's what I'm thinking. They started off, right, by looking at the demographics and showing that they were the same or not significantly different across the 2 groups. What do you make of that, or why do you feel that might be important, or anything? Do you have any thoughts about that?
Why do I think that the demographics were similar, or what?
Why do you think that showing that was probably a good idea?
I mean, they were all college students, so in my mind, I'm thinking that college students are generally around the same age. They're generally in similar SES. So I guess it's important to note, just we can't really generalize these results to another population or a minority population or a special population, I guess you could say.
Absolutely. I think that's right on. I think you're raising some really good points that, if we're looking at these 2 groups, we'd like to show that they're similar to each other, because we're trying to differentiate them on hopefully just the one point, on hopefully just suicidality, right? On suicidal ideation. So ideally, we'd like to kind of show that they're similar in other ways, but just on this one point, they're different, and that's what's influencing the other variables. So yeah, I think you hit that well. one other point that I just want to raise for everyone is you notice that they used a p-value, an alpha really it looked like, of 0.01 rather than 0.05. And yeah, because they kept comparing it to less than 0.01. At least that's what it seemed like. So the reason I think they did that is because they had so many t-tests they were running. And the reality is every time that you're running a t-test, you're really increasing that alpha. So if you continue to run a whole bunch of t-tests on the same data, you're kind of increasing your alpha. You're kind of taking a little bit of a risk with your type 1. And the way to counteract that is to then lower that alpha down to 0.01 rather than have it sticking out there at 0.05. Now, in my mind, they could have actually lowered it even just a little bit more, but we can talk about that another time. Anyhow, very nice job, Lindsay. Thank you so much.
Thank you.
Okay. And
Is it my turn?
Justin, are you ready?
I'm ready.
Okay, whenever you're ready.
I'm ready. Okay. Yeah, move your guys' faces out of the way. Okay. I'm Justin. I'm going to be presenting on the Mann-Whitney U article. The title of the article, Shorter REM Latency in Children with Attention Deficit Hyperactivity Disorder by Diaz-Rahman and Ouellet Casal. Here's a quick summary of the article. The goal of the study was to compare subjective and objective sleep characteristics in 20 children with ADHD with 20 children who are typically developed or non-ADHD. They were all aged 7 to 11 years old. The data was gathered using the PDSS, the PSQ, and a sleep diary, which were their subjective measures, and PSG recordings, and that included a whole bunch of different measures like total sleep time, sleep efficiency, REM sleep, REM latency, and more. And that was the objective characteristics. The researchers expected to find more sleep problems in individuals with ADHD compared to the control group. They found statistically significant differences in REM latency, looking at the PSG recordings, where children with ADHD had shorter REM latency compared to the control group, and statistically significant higher ratings of daytime sleepiness and general sleep problems in ADHD children compared to the control group. Surprisingly, there was no statistically significant difference for all of the objective PSG measures except for the REM latency, as I discussed, and there was no differences between either group's sleep diaries. So, as I said, the Mann-Whitney U test. Here's a picture of their results. Hope you can see my mouse. This is the PSG, the objective measure they used, and all the different factors that looked at. And here are the subjective measures, the daytime sleepiness, general sleep problems, and the sleep diary. I don't know why it's cut off the bottom there, but you'll see these asterisks here indicate the statistically significant scales, and it's just the general sleep problems, the daytime sleepiness, and the REM latency. So the independent variable are children with ADHD and children without ADHD. And they looked at the subjective and objective sleep measures, so all of these. And the results they found, as I said, REM latency with a p-value of 0.006, daytime sleepiness with a p-value of 0.010, and general sleep problems with a p-value of less than 0.001. All the other measures they found that had a p-value of greater than 0.05. So here are the null and alternative hypotheses. The first three, we're going to reject the null, and this bottom two, we're going to fail to reject the null. They all follow the same format, similar to Lindsay's. The null, there is no difference in REM latency between children with ADHD and children without ADHD. Alternative, there is a difference in REM latency between children with ADHD and children without ADHD. And then there's daytime sleepiness, general sleep problems, and these are the three that they found were significant once again. And then here's two of the other objective measures they looked at, time in bed in minutes and sleep period time in minutes as well. So this was a two-tailed Mann-Whitney U test. It's two-tailed because they were just looking for a difference between the two groups. They were not looking for a specific direction. So was this choice to use the Mann-Whitney U test appropriate? Yes, it was appropriate because, as they mentioned, it did not meet the assumptions for parametric statistical tests. One of my concerns or problems with this is they didn't really talk about what assumptions it failed. There was no, box and whisker plot where we could see an outlier or anything like that. They just literally said a one-sentence statement. It didn't meet the assumptions. And some concerns I had with the rest of it, not specific to the Mann-Whitney U test, it was a small sample size with only 40. From what I can understand, that's somewhat normal with these kinds of studies, 40 participants. But you always want to see a bigger sample size. And they discussed the limitations, including the various subtypes of ADHD that could play a role. Medication. They did take all the children. There are 17 of the children who were medicated who had ADHD. 48 hours before they had all the EEGs set up for the objective measure, they took the kids off medication. But in some of the medications case, not all of it's going to be out of their bloodstream. And if you've been on medication for years and years, and one day you're just forced off for a weekend, I can imagine that has some complications with results. And they also talked about SCT in the study. And comorbid conditions could play a role. They talk about conduct disorder. What else do they talk about? ODD. They talk about a couple of different disorders that could play a role. They didn't look at these. With the Mann-Whitney U test, they just mentioned, it could play a role. And just the concern is the results this study found were not consistent with results from other studies where they found a lot of these differences were actually statistically significant. So why that is, maybe because of the limitations, maybe the sample size, maybe something. But yeah, this study in particular did not have similar results with other studies. And that's all I have. Any questions?
Well, thank you. That was a great presentation. I thought you pointed out some really interesting limitations there. Especially with the comorbid conditions is kind of interesting too, like that was potentially there, but they didn't adjust for it or account for it. So yeah, I think the choice of Mann-Whitney U, and we don't know yet what the other choices are, but the choice of Mann-Whitney U, they could have done something a little bit more interesting to include some of those variables and account for them. Mm-hmm. So I think you raised some interesting points there. Is this your area that you knew about some other articles that conflicted, or did you just check into it?
No, it's actually something they talked about in their limitations.
They did. They talked about their limitations. Okay. Yeah. Cool.
They proposed results and had a bunch of different articles that I briefly looked through because their hypothesis of, individuals with ADHD have more sleep issues. Other studies found that to be true, whereas this study, they found not so much.
Okay. And did they specifically say what their alpha was in this study?
Yeah, they did. I don't know why my picture got cut off.
Oh, they did in that one that got cut off. Okay.
But I don't know why. I thought I took a good screen.
No, that's okay. The reason I ask is it comes up with the same issue that Lindsay's article had, and that's, with all of these tests, the fact that, there's got to be, how many are there here? I'm wondering. At least around 20, maybe?
That looks right to me.
Yeah. Okay. So, they probably should have, hadn't even, had not counted that 0.10 for sure, I think, because that strikes me as a little bit high of an alpha to be counting with this many tests. So I thought that was an interesting point that comes up here yet again. In comparison to Lindsay's article. Any other questions or comments for this article or for Justin?
Thanks, guys.
Okay. All right. So, very nice presentation. Thank you. And let's go ahead and turn back to our review. And let me just open it up to any questions that you guys might have about any piece of it. So basically, we covered everything. We reviewed everything except, you know, we didn't redo the most recent stuff. I tried to do the more complicated pieces, the pieces I thought you might get stuck on. But if you're going back and reviewing, then lecture 1 and the first 20 odd slides of lecture 2 I didn't cover. And of course, I didn't cover the most recent stuff that we just went through. But anything in there, anything else you want me to review, just, I'll be quiet now. You can go ahead.
I had trouble with, I think it was number 2B on the last homework that we just did. Do you mind
Okay.
like going through that?
Not at all. It'll take me a minute to pull up the data. Give me a second. 2B on the last homework we just did, right?
Yeah, I think like my confusion was around, I think the Shapiro-Wilk like showed normality, but there was like one outlier. So I ended up just saying that like the outlier could stay because like Laird said that was okay, but I wasn't sure if that was the right thing to do or not.
Oh, yeah, let's look at that. That'll be interesting. So 2B, let me pull up the data. Sure, yeah, go ahead. And let me share my screen with you. Actually, let me run the, let me set it up real quick. Actually, I'll share my screen throughout the process so you can just see in case you're interested. More interesting than looking at nothing. So here's my screen. Okay, and I'm gonna kind of scoot you over a little bit here. Okay, great. So now the first thing I need to do is create my diff variable. So I go into transform, compute variable. I've got my diff equals time 1 minus time 2. I could have done time 2 minus time 1. Either way is perfectly fine. Okay, and I have some old stuff over here. So let me clear my output real quick. By the way, that's a way to clear your output. You could also close the window, but you could click on just output and hit delete, and that'll get rid of it for you. Of course, you couldn't see that because you're stuck on my data, aren't you? Yes. Okay, so I have my data up here. I'm now going to analyze, going under descriptive, going under explore, putting my diff in the dependent list, going under plots, making sure I have my normality plot with tests. I'll hit continue, and then I'll hit OK, and then I will switch over so I can show you my output here. As soon as this lets me, new share to the output. Here we go. Okay, hopefully you are now seeing my output for this. And you're absolutely right that according to Shapiro-Wilk, the normality looks fine. And then we get to there we get to the box plot. That's a toughie. Yeah, because it's negative, it's out by -10. This is case number 11, and I can just see looking across that it looks like the value is close to -10, which is really quite low for this. So the short answer is I think it's debatable as to whether you go ahead and run the Wilcoxon or stick with the t-test for dependent samples and go ahead and, you know, just say, I'm going to leave the outlier in. Something else you could do, and this is probably what I might do if I was faced with this in a real research situation. I would run it as so a couple options. I could run it both ways. I could run it with the t-test and Wilcoxon and show probably that I'd get the same results for both. Or I could run it with the t-test for dependent samples with and without the outlier. And I think it might be worth showing you if you ever need to exclude a case, how you can do that. So of course I could simply delete this case, right? I mean, I could get rid of it, but there's another way. There's a data, select cases, and I could select, sorry, are you seeing this select cases window that just popped up?
Yes.
Yes, okay, thank you. So I could say if the condition is satisfied, if diff equals -10, let's say, continue, and then I could, I should have said if it's not equal to 10. Yeah, sorry. If df is not equal to 10, let's try that again, not equal to -10, then I will filter out the unselected cases. Let's see if it did this correctly. I have my ifs and not ifs on board, yes. So what it did is it took out that one case so that if I wanted to rerun it now using the same thing, I could. And the truth is, most times, more often than not, you get the same results when you do these different games, if you run it with both kinds of tests, or if you take a score, take a case out and rerun it. Oftentimes you wind up with at least the same significance, that if you're going to reject, you still reject, or if you're not going to reject, you still don't reject. So there are some options there. But like I said, I think this one was a bit of a toss-up in terms of how you might proceed with it. But I think it raises some really good points. So thanks for bringing it up.
Thank you. Did you say which like numbers of these past two homeworks that you were grading? Like how last time you told us you were grading like the last, I think it was item 9 and 10 on the first two homeworks.
That's right. We haven't gone through that. Yeah. How about it for these two? There aren't too many of them, right? There's 2A, 2B, 8A, 8B for both weeks. So that's not too bad. So rather than pulling a random on you for this one, we might do it for others. How about if I just take a look at everything, and that way you get the benefit of feedback across the board.
That sounds good to me. I had another question along.
Yeah.
For homework 3, Lynch's question actually made me think of it. I think it was the fourth question. It was talking about online classes versus traditional classes, and the variable was grade, so 0% to 100%.
Okay.
One of the data points was 120%. So that is obviously more than 100, and it was an outlier. And so you would think the Mann-Whitney-U test is the go-to, but with it being over 100%, where the 100% is a max, assuming there's like no extra credit or anything like that, would it not be best to just delete that one and keep going?
Yep. That would have been the approach I would have taken for that one, because the 120% was clearly, and you're right, assuming no extra credit, right? So we do have to make that, we'd have to know for sure. So if you had this data and you knew, oh, there's no extra credit here, what's going on here? This person got 120%. What was that supposed to be? 20% or 12% or 100%? You have no idea. So if you have absolutely no idea what to do with that data, I think the best thing to do in that case would be to eliminate that case, then run your explore, and then see which test you're going to run. So that's a tricky one also. I think that's a good one for discussion. Now, if you left it in and then decided to run the Mann-Whitney, that's no big deal. But I think it's a good thing to be aware of, like to grow in that direction of starting to have a sense for like, okay, what is my data and what's real and what's not here, and what's important to you know, just like, let's understand my data, let's be in with my data, and get a sense for what should be here and what shouldn't be here, is what I'm trying to say. Okay, so thanks for bringing that one up too. That's a good point.
I have a question for the most recent homework. When you run the Wilcoxon, I bought that version of SPSS. I don't use the RamCloud one, and I was having a hard time finding the test statistic.
Yeah.
So I think I ended up just running it the two different ways, like the legacy dialogues and then the other way, and I found like a test statistic, and I'm assuming that was the W that we were looking for.
Yeah, I just ran into this today, where someone had a similar question along this line. So yes, let me pull up this real quick so I can run it along and we can kind of take a look at it. So let me go back to the homework. And you said this was homework 4 or homework 3?
Homework 4.
And do you remember which one it was?
I
I guess it
think.
doesn't.
Yeah, I don't remember. I'm sorry.
That's okay. I'm just going to run 8A. It's fine. It doesn't really matter. I'm not going to do the pretest. I'm just going to go ahead and run the Wilcoxon so we can look at this, because it's a specific issue. So analyze non-parametric tests, and I should have the same one as you guys. Related samples automatically is fine. Field satisfaction 1, satisfaction 2, settings. Sometimes I like to make sure it's going to run what I would like it to run. So I'm going to go ahead and check off that Wilcoxon. And then I got to get this out of the way so I can actually run it. Run. Okay. So that's using the normal one. And yeah, they did make a change to this. It used to be when you double clicked in this, you got all this other stuff. But the test statistic should be this 628. Now let's double check that and see that.
I can't see your output. I'm sorry.
No, I'm sorry. I keep forgetting to keep switching back and forth between them. Okay, hopefully you can see it now. If you can't, someone shout. Okay, so here is the output, and the test statistic, I believe, should be the 628. And if we ran it, I think what you said is you ran it as the legacy. So if we actually did that, analyze non-parametric legacy, come on, 2 related samples, satisfaction 1, I'm in class, Chris. Sorry, that's my son. Okay, so let's continue, and let's actually go ahead and include these descriptives just for fun. Let's continue Wilcoxon and hit OK. And I'm just trying to see if it's giving us more here or something better here, and not really. With the legacy, at least I'm not seeing it yet. Yeah, here's the legacy one. And while it's giving me a couple of interesting pieces here, it's not actually it's giving me the Z, which I had up here anyway. I'll show you. Here it is. Here's my Z. And the negative positive is just how you put it in the order. So I'm not worried about that. So I think the main way to get the test statistic is to not run the legacy and run the current one. So is that not your experience, or did you get something different, or was it just hard to decipher?
It was just hard to decipher. I just was unsure Because I think in your slides you had an output that had like W or whatever it was.
Yeah, I think they changed it in this version. So
Yeah.
I'm sorry about that. But yeah, but for future reference, and that this is where it counts, yeah, your test statistic would be the one you'd want to report.
Thank you.
Yeah, of course.
I have a question about that. In layered, they don't like in the sample like of the results, like how you
Yeah.
report them, they don't actually report that number though, as far as I can see.
Oh, I mean, yeah, that's probably a bit of a toss-up. I mean, the Z is probably more important to report, and of course, the p-value you always want to report, because the Z is a nice standardized number for you. I have seen articles where they do report it. I would probably go ahead and include it for completeness. I don't think it would be, tragic if you didn't include it, but I think it's nice to include for completeness sake, really. But I don't think it's like the most important number that you're reporting.
Okay, just letting you know that's if you look at my homework, I probably didn't include it.
Oh, that's
but
fine. I mean, again, I wouldn't worry too much about it there. This is where we're kind of coming to some, understandings about things. So yeah, don't worry too much about that.
okay, but for the exam, like we should include it.
Yes, please go ahead and include it.
Okay, thank you.
Sorry, this is me going back to, I think, one of the first questions regarding the outlier and whether we should proceed with the Wilcoxon test or not.
Yeah.
But was it debatable just because of how far out the outlier was?
Yeah, had they been a bit closer, I might have been more like, yeah, it's okay. We can let the outlier go. For the most part, I mean, and if there was more than one outlier, it would be a clearer decision to be like, yeah, well, let's move on. Let's move on to the Wilcoxon. But since it was just one outlier, had they been closer in, I would have been more inclined to be like, it's okay. Had they been even further out, I would have said, no, but it was just right at that point that I was kind of debating it. So yeah, that's why. But if you went cautious and went with I mean, I think that one, like I said, is truly debatable, but I guess if you're stuck in that kind of situation, I'm going to urge you to just be on the cautious side, like going forward for the exam or whatever, or in life, to just probably play the cautious side and go ahead and run the non-parametric test.
Okay, thank you.
Sure. just so you guys know, I'm happy to continue to hang out, and I will hang out if you're like looking through things and trying to decide about other questions. But if you are feeling set at this point, please feel free to take off and have a great night. But I'm here, so please feel free to keep the questions coming too. I see a question coming through. Oh, okay. Sounds good. Have a great night. Hi, Lindsay. It looks like it's just the two of us now.
Sorry, my mouse is being really laggy, so I'm trying to get to the mute button. I can't get there fast enough.
No, that's fine. No worries. Do you want to ask more questions? Do you want to talk about the paperwork you submitted earlier? What would you like to do?
Yeah, I kind of just wanted to like touch base about like the letter and like what that means for the exam.
Yeah. So that's a great question. Because what it means for so first of all, I mean it says a distraction-free environment, right?
Mhm.
And you can take it at OSSD, I think, if you want. So I guess the first thing we should figure out if that's something you want to do, or do you just want to be online with everyone else, or how would you like to work that?
I'm just thinking I'll just take it online with everyone else.
Okay, so then the next issue is that you get double time. And I might be forgetting issues, so please jump in. But I know you get double time. So that would be 5.5 hours, which is a long time to sit for an exam. So I don't know what you want to do, like if you want to like take part one with the class and see how it goes, and then if you need a break before part two, we could schedule part two for like the next day or something. Like that's something we could do. That's just off the top of my head is one idea. It would be nice if you were able to complete each part in a sitting, but I mean, if you feel like you can't do that either, we'll work it out.
Okay. Like, is there a way that we could like figure that out on the day of? Because like today I have like a really bad headache. I think just because like we have like this class is later and like we have another class before this and I have like other meetings like all day. So like it just depends on how I might feel like that day. So is there a way that we could say like I'll do part excuse me, I'll do part one and then like if I could take like maybe like a 20-minute break before part two, but I could still finish part two the same night.
Of course, you can do any of those things. Yeah, absolutely. Yeah. Yeah, let's work it out that day. Let's see how you're feeling. Let's see how you're feeling, that day, and then also after you complete part one. And if you're feeling like I've had it for tonight, then let's schedule for, preferably another day close in time to the first day. But certainly we can do it another day.
Okay.
Or we can take
And
a 20-minute break or something, as you said.
you're usually available on Fridays, right?
I'm usually,
Like
I'm sorry?
your office hours you have Fridays, like sometimes you're
do.
usually available on Fridays.
Yes, but that's only a 2-hour stint, and again, you might need longer. So I have a lot of time actually on Thursday. What are your Thursdays like?
I am not available until after 4:30.
Okay, so that's a possibility, but if late's worse for you, then that's probably not a good possibility. But we could make that, we could definitely do after 4:30 on Thursday or Friday. I can open up a Zoom room for you between 11 and like 1:30, 2.5 hours. That might be enough time? And if not, we'll rework from there. But I could do that.
How many like of those type of like the SPS output questions are there?
That's a good question. Probably somewhere around the 5 neighborhood. Could be a little less, could be a little more, but probably somewhere around 5.
Okay, because I'm wondering like when I do the homework and there's 4, like is it the same type like of similar to the homework where you're like saying the hypotheses and then like your results for the test?
Yes, it would be a similar type of approach.
Okay, so I usually do like since there's 4, I usually do like 2 and then I have to take a break.
Yeah, and do
So
2.
like
Okay, we can split up part 2 as well. I mean, if you need to. What I'll do, I'm glad we're talking about this, because what I'll do is I'll only like give you 2 at a time, maybe. And then you
okay.
just keep coming back to me as you're ready for more.
Okay, so then maybe like I could do like part 1 and then half of part 2 on Wednesday night and then
Mhm.
we could finish on Thursday or Friday.
That works.
Okay, that sounds good because I don't think I can sit through the whole test in one night right now. But
Right.
I might feel differently next week. So if I could let you know if that's not too late, if I could let you know
Yeah,
maybe.
we can work this out. Yeah, yeah. Just keep me like kind of up to date if you can, and we'll work out the rest.
Okay.
And I'm trying to decide. It's hard for you to, part of it was not being on camera as much, right?
Right.
Okay, so if you need to be off camera for any part of the test, just turn off your camera.
Okay. So everyone else's camera should be on the whole time because I don't want people to think I'm like, being shady or
Yeah, I
anything
know.
either.
I understand. And that's what I was trying to get at. Like, it's gonna bug you even if you're looking down, right? It's probably still gonna be like,
I don't know. I mean,
yeah, it's hard to know. I understand. So I don't know. I had to think about that one. My feeling is I'm okay with you having your camera off if you need to, but I very well might ask everyone else to put their camera on. And it's because of I want to be respectful of your accommodation though, and I want to, the last thing I want is for you to take this test under duress, or under bad circumstances. So, I want it to be as fair as possible. But I can think about that more. It's late at night. I might not be in my most creative mode right now, and maybe I'll have a better idea of how to handle that going forward. Another possibility is you could take the whole test at a different time. I mean, we could work that out.
okay. Yeah, I mean, we can both think about it a little more and talk again like early next week too.
Yeah, let's do that. Let's do that. That sounds good. What other accommodations am I missing?
I'm pretty sure that's it.
Okay.
Let me just double.
Oh, there was something about emailing you the slides. I post them on D2L. Is that sufficient, or do you want me to send you an email copy?
No, that is sufficient. That's more geared towards like professors who just come in with the slides without having posted them because I'm not supposed to be looking at them on the screen. So
Oh, okay.
if they can be posted, like if you're posting them in advance enough for me to print them, basically, that's fine.
Okay. Gotcha.
I don't know if I didn't print them today because I'm waiting for a printer to come in, so it doesn't matter for today, but
Okay. All right. Well, going forward, if I'm running tight, I'll just email them to you as well, so that you have them. Or I generally don't change much, so you might be getting like a penultimate version that maybe a slide or two is different, but the rest are the same or something like that. But I'll make sure you're getting them.
Okay.
Continue to talk about that too if it's not working out.
All right. That sounds perfect.
Okay, great. Good. Yeah, I hope you start to get to feeling better. I hope the appointment you had earlier went well, and you know you're on a good path now. So, anything else you want to discuss tonight?
No, I think that's it. I really appreciate like how accommodating and flexible you've been so far.
Yeah, no, that's fine. I certainly can understand how it can be really difficult. Yeah, to go through something like this and to be taking grant at the same time is less than ideal. So yeah, we'll make it work. We'll make it work. So let's talk again early next week. And we will figure something out as to where we're heading. And I guess just have a great night.
All right. Thanks. You too. I'll talk to you
Okay.
soon.
Okay. Bye.
Okay. Bye.